Hello, and welcome to Game Revolutions, the series where I take an assembly language game that I started in high school and see what improvements I can make now. Although not originally intended, I slowly yet surely am systematically rewriting every line of code. I'm sorry, younger self. I can't help myself. I've learned new ways of doing things, and I want to do those things. In past episodes, I had temporarily disabled some game elements so that I could add double buffering and stack blasting. Then I started to re-enable those game elements, and then I ran into weird performance issues. And in the past couple episodes, I diagnosed and fixed one of the weirdest performance issues. Now I'm kind of on a speed kick, and I'm curious to see what else I can make faster. And thanks to viewers just like you, there are comments that are pointing me to areas that I can improve. And today, we're going to look at one of those comments. I'm going to go through several iterations to see if I can actually follow the comment properly and get some performance wins. Along the way, I'm going to be doing a lot of cycle counting. So if you are a fan of elementary school arithmetic, don't touch that dial. Lost Wizard asks, have you checked to see if it's faster to do that row of ground manually instead of all the setup for stack blasting? It's only 16-bit load store operations, which you could unroll. As you may recall, we're only doing one row of ground now. The rest of it is done kind of manually. Some of it is red and it just doesn't move, and some of it's the mile markers, which we do on their own. Could I do that one row of ground quicker if I just did it the normal person way and not the stack blasting crazy person way? Here's the code I came up with. It unfortunately is not unrolled. The reason is that since the ground is rotating, I'm using this as my offset to tell me where the ground is supposed to begin on any given frame. And so it's split up into two loops, one that copies everything from this offset to the end of the buffer, and then the second one which copies everything from the beginning of the buffer up to this offset. That buffer gets included right here directly into the code, and it consists of these 32 bytes. This is similar to how the mountains bytes are included. They're included here, although of course there are far many more bytes for the mountains. The rot offset travels through this buffer. So for example, if the rot offset were over here, then the two regions we'd copy were everything from here to the end. And then the second one would be from the beginning up to that rot offset. I'm not sure how to unwind those loops, given that they will have an arbitrary number of bytes in each one, depending on the frame. It's even worse than that. Sometimes they're going to have an odd number of bytes, sometimes they're going to have an even number of bytes. So I can't simply do a loop that does 16-bit copies each time. So what I've done is I've done loops which do 16-bit copies each time, but has a little fix-up beforehand. So this copies the first portion, which is from the rot offset up until the end, and X is pointing to the source buffer that contains the bytes to copy. U is pointing to the portion of the screen where the bytes go. So X begins where my buffer begins, plus the offset. And then I do that loop. And then at the end, I change X to point at the very beginning of the buffer. And I loop to do the copies until I reach this value, which is the beginning of the buffer plus the offset. The stuff I skipped over deals with the case where it's not an even number of bytes I need to copy. I can look at my offset and ask whether the offset itself is even or odd. Since I'm copying 32 bytes total, if the offset itself is even, then that means both portions of the copy will have an even number of bytes. If the offset itself is odd, then both portions of the copy will have an odd number of bytes. So in the case where it's odd, I just do one byte first. So I guess I kind of unwound it, sort of, by one. And once I copy that one byte, I'm now ready to copy an even number of bytes to fix it up. And again, in the next portion, if the offset is odd, I will do 1 byte before I do my loop that does 2 bytes each. I'm guessing this has more code, more fix-ups than Lost Wizard was expecting, and in fact, perhaps more than is necessary. I could be doing this suboptimally, but this is the best that I've come up with. Let's see how it fares. Once again, we're going to set a breakpoint just before the sync. That's 3E79. As you'll recall, most of the time the beam Y was at 137 using the stack blasting method for everything. Now we're using the straightforward copy for the ground, but stack blasting for everything else. We're at 138, 138, 139, 138, 139, 138, 139. So it's worse. Now we do go down to 129, but as you recall in the old method, we also went down by 10. And that was due to the offset being right at the beginning of octet 1 or 4. Back up to 138, 139, 138. So it kind of seems, using this as a very coarse performance gauge, that I made things worse. I don't fully trust this with something that's so close, so we should do some cycle counting. As you may have noticed, I've been sprinkling some of these pragmas around so I can get some cycle counts out of this. CD will give me the cycle count for each instruction, and it will detail it down. It'll add the base amount plus whatever extra amount depending on the addressing mode I'm using. CT will also give me a running total, and CC at various points will clear that running total. So that'll allow me to get chunks of code and get totals for those chunks. So starting with my new code, these are my individual cycle counts and these are my running totals. So in rotate ground top, we first have the initialization code just before the first loop, and that totals about 57 cycles. I should note, by the way, I'm not being completely 100% perfect. Not all of these instructions have exactly the counts that you're seeing. It depends whether or not a branch is taken, and whenever there are loops, I'm going to be estimating as well. But I'm going to try to rough it, but not be too inaccurate. So we have 57. And then the first loop, I've cleared the counts here. So the first loop, each iteration 23 cycles. And of course, this iterates a variable number of times. But you know that the first loop and the second loop total will iterate 16 times because we've got 32 bytes and each iteration of each loop does 2 of those 32 bytes. So there's a total of 16 bytes to be copied. And so what I could do is just allocate 8 iterations for the first loop and 8 iterations for the second loop. And again, I'm roughing it because sometimes when there's an odd number of bytes, this is going to happen. And that's going to decrease this or the other count by 1, but whatever, close enough. So to our 57, let's add 8 times 23. And then we have the prep for the next loop. That's another 35 cycles. And then this loop is 26 cycles times 8. Now you might wonder, why is this more cycles than this? And the answer is my boundary condition here, I can use immediate addressing mode because I know exactly where the end of my buffer is. Here, the end of my copy is going to be a variable amount. This is going to be the beginning of the buffer plus the offset. Now I could use self-modifying code to, instead of doing this, make this also be immediate addressing mode and then like poke into here the calculated value. But can we please just keep on going here? For crying out loud. Just going to ignore the RTS for now. And let's leave it at that. So that gives us a total of about 484 cycles for the new way. Let's take a look at the stack blasting way. I've kept the old stack blasting code and the calling code inside the file. It's not even commented out, but it's just never called. This way, as I do the assembly, I can do the counts for them as well. So the cost to call the stack blasting code is all of this preparation, and then one of these 4 octet cases. So recall that each of these octet cases initializes things like which buffer are we going to copy from and whether or not we're the leftmost octet in that buffer. So what I'm just going to do is take the prep code and then add this first case all together. And I'm going to call it 68. The other cases are very similar, not exactly the same, but they're very similar. So figure 68 just to get ready to call the stack blasting routine. And here we are in the stack blasting routine. So first we've got some initialization to do before we start our loop. And so the initialization, if we go down, bloop, 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 that gives us 110 cycles. And then we have our loop to do the stack blasting. And you know what's cool, folks? This is not a loop. It's just one line of ground. So I don't have to do any weird estimating or hand waving. I can just count all these cycles, and that's how long it takes, more or less. Not exactly. Give me a break. Okay, so restarting our cycle counts here, clearing them. We're going doot, 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 doot. You'll see there are cases in rect1 and rect3 where we copy a variable number of bytes. We use self-modifying code, which I already counted to poke a different address here. I'm going to include the count to do the jump, and I'm going to include the count for where it went to later. So for now, don't worry about it. We'll come back to it. But we're going to keep on going. Doot, 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 doot. Oh, look at that. All that stack blasting. That's some good stuff. Doot, 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 doot. Okay, so then we come all the way down here. We're done with the loop. And then we come down here, and then we do this. I'm going to call it 186. I didn't count the RTS in the first one. I'm not going to count the RTS in this one. So let's add 186. All right, so that leaves these two jumps for rect1 and rect3. We know they're going to copy a total of 8 bytes. It's going to vary, so this will do maybe 2 and that'll do 5, whatever. So why don't we just see what it costs to do 4? So copying 4 bytes is going to be 9 plus 9 plus 4. So that's going to be 22 cycles. And we'll add that in twice, one for rect1 and one for rect3. And that gives us a total of 408 cycles, as compared to 484 the new way. But that was all dumb, because there's obviously a better way to do the copy. And by obvious, I mean it was obvious to me after I did all of that and recorded all of that. What I've been doing is I've been using this buffer as the source. So I would start at the offset, go to the end, and then go from the beginning to the offset. But this doesn't have to be the source every time we rotate. I could use this to populate both of my screen buffers, and then do a copy within the screen buffer. I could just use each screen buffer as both the source and the destination of the copy. I grab a byte, copy it to the left, grab a byte, copy it to the left, and so on. Now, of course, I've got 2 screen buffers, and so just as I was doing with the mile markers, I have to actually copy it 2 slots to the left and not just 1. So I've updated this drawStatic2 routine, which is responsible for doing all of the static non-moving portions of the screen, like the yellow stripe at the top and the blue and the green that don't change. And I've added it to pre-populate the buffers with the gravel at the very top of the ground. It's called once for the first buffer and again for the second buffer, and you'll see just before I call it for the second buffer, I increment my ground rotational offset. That way the second buffer will be 1 frame ahead of the first buffer in the animation. So in drawStatic2, just after I'm done doing the static red portion of the ground, just above it, I call the old stack blasting code to just do that line of gravel at the top of the ground. And this will get called again once for each buffer, with each of them differing by 1 frame. So that bootstraps things. And here's the new code to rotate that ground top. I point X to be the very leftmost byte of the gravel. I capture that leftmost 2 bytes, because since we're doing a rotation, the 2 bytes on the left are going to end up being the 2 bytes we want on the right. So I store that here, which is actually self-modifying code at the end. So this is where I'm going to load D with that value to store it back on the right-hand side. And then I figure out where the endpoint of my loop is going to be. That's going to be X plus 30. We're going to go up to X plus 30 because at X plus 30, that's where we're going to copy that byte that we just stored. We load U with the endpoint of the loop, and then I store that endpoint using self-modifying code right here. And now we're ready for our loop. With whatever word is at X plus 2, copy it to X, and then advance X by 2. And once again, we're advancing X by 2, and we're using the source of the copy for X plus 2, because each of the 2 screen buffers advances by 2, because we alternate them. We compare X with the endpoint, and then we loop back up if it's still lower. And then finally, for the wraparound, We load D with that value we saved from the left-hand byte, store it where x is pointing now, which is going to be x plus 30, and we're done. Where is our beam y now? It looks like it's 136, 137, okay, I'm not going to count the ones that are 10 below. 136, 137, 136 looks a bit better by maybe almost a full scan line. Let's count those cycles. First, we have the code that prepares for the loop. That's 36 cycles. Then our loop itself is 21 cycles per iteration. And it should iterate 15 times because we're going to go up to an offset of 30, because at 30, that's when we're going to do that final byte or the final word that wrapped around. So we multiply 21 by 15. And then for that final word, we have another 8 cycles. As before, I'm not going to include the RTS. Grand total, 359, a definite improvement over the stack blasting code, which was 408. But we haven't even got started yet, folks, because now that I have a loop that runs a definite number of times, I can unwind it. So with the loop unwound, it now looks like this. You'll notice I don't have to do any work to grab that endpoint for comparison because there's no loop with no loop condition. All I do is I take whatever is at 2 plus x, copy it to x. Whatever 4 plus x goes to 2 plus x. Whatever is at 6 plus x goes to 4 plus x. Whatever is at 8 plus x goes to 6 plus x. And so on and so on and so on and so on until we get to whatever was at 30 plus x goes to 28 plus x. And then at the end, we write to 30 plus x, whatever was on the leftmost side that we wrote here to remember for later. This might be an extreme form of loop unwinding. People will sometimes, rather than unwinding the entire loop, maybe they'll unwind, say, 4 iterations or 8 iterations and then loop that. That way you get a balance between fast code and small code. But for now, I'm on a fast kick, so I'm just going to keep it fast. And if I need to reclaim more space, I know this is one place I can go to later. So now our scan line gets up to 134, 135, 134, 135, 134. Counting cycles is now easier than ever before because there's no loop. There's no weird this, weird that condition. I can just let LWASM add everything together. So tell us, LWASM, what do we get up to without counting that RTS to keep things consistent? 213 cycles! That's only a little more than half the cycles it took to do it with the stack blasting way. Almost as good as half. This was a good idea. Thanks, Lost Wizard. It took me a while, but I think we got there. Well, that was definitely some good advice. I am very happy with the gains that I got by following that advice. But that's not the only piece of advice I got. So in future episodes, we're going to take a look at another comment and see if that will help as well. Until then, thanks as always for watching.